Let's talk about a very important concept in mechanics, which is called center of mass. A lot of Lagrangian mechanics becomes very easy if you know the center of mass of objects. So what is center of mass? In physics, in mechanics to be precise, the center of mass is considered to be the point on an object where it is assumed that all the mass is concentrated at. For point objects, you can think that the center of mass lies at the location of that point. For symmetrical objects, you can think that the center of mass lies at the axis of symmetry. Center of mass, abbreviated as COM, C.O.M, you can think of this as a vector quantity because it associates a location as opposed to a direct magnitude or an only magnitude quantity. So it is a vector quantity, you could say. So let's think of center of mass with some pretty pictures. Now think of the following. You are located at the center of a coordinate system in, let's say, x and y plane, and you are located right over here where you consider yourself to be at the origin. Now, you are a part of a system that has 3 point masses. Let's say one point mass is over here at M1 at R1 location, denoted with a vector. You have another quantity, another mass, M2, that can be associated with the vector R2, the position vector R2 to be precise, and the other mass, all point masses, the third mass is located at position R3, the position vector R3. So you would define the center of mass of this entire system as to have center of mass RCOM to be at M1 R1 plus M2 M2 R2 plus M3 R3, all divided by the sum of all the masses. Okay, now this is for just 3 masses that you can see over here. What if I have n masses? Let's say I have many masses, many point masses. So for the case of n point masses, you can write this expression RCOM as, all right. Now, you don't want to write this as the sum of n masses all the time. So here comes math to simplify your life, and you can simplify this whole equation to look like some sort of a summation notation that goes from I equals 0 to I equals n, all divided by mi's, going from I equals 0 to n. All right. There's a popular integral form that we often use to describe the location of the center of mass for rigid solid objects. And the integral form has the following form, where when you're doing the integral, this vector r denotes the position vector of each of those point masses called dm, right? Another popular notation or another popular form of the center of mass equation is when you express this dm over here as a function of the volume and the mass density. So you know that that the mass density rho is defined as dm over dv, right? So you can isolate the dm, and write this as rho times dv, where rho is the mass density. So when you have the dm, you can basically put this dm inside this equation over here, and you can write that rcom, or r center of mass is 1 over m times rho r dv. Okay, so yeah, so basically we have these forms for the center of mass. One that you can write down with the summation notation, the other one which is basically this one you can write this down as with the integral form, and the other one which we just wrote down over here as a function of mass density and volume. Okay, now let's look into a more concrete example where we are trying to find out the center of mass of a particular solid object, for example. Okay, so let's do an example where we are asked to find the center of mass of a solid cone. As you could tell, the solid cone that you see over here has a symmetry about the z-axis if we consider this dotted line to be the z-axis. So since the cone has a symmetry about the z-axis, we could tell about symmetric objects that the center of mass must lie on that axis of symmetry, and in this case it is the z-axis. So all we need to do to find the center of mass is to find the center of mass along the z-axis. All right, so as much as we remember from the formula, the center of mass formula around any axis given is given by this equation over here. I'm writing z because we're trying to find out the center of mass along the z-axis, right? So we can also write this down as 1 over m and then times the integral z rho dv, where rho is the mass density along the z-axis. Okay, so you can write this entire expression down as a triple integral because you can write dv as dx, dy, dz. This is supposed to be a triple integral that should look like the following. Oh, this rho over here is a constant, so you can pull this out. And this kind of looks like this. Z dx, dy, dz. Okay. So let's think about how we could solve this. Now, we could solve this in Cartesian coordinates, but it becomes very much easier if we switch coordinates over to spherical coordinates. The infinitesimal volume length, dx, dy, dz, we can figure out what that is in spherical coordinates. So the dx, dy, let's think about the dx, dy. You can think about what this dx dy infinitesimal patch of area is if you look at the solid cone from the top. So if you look at this from the top view, what you will have is these discs, these discs over here that look like circles. So from the top view, what you'll see is these circles, where this is the center, and you have these small patches over here. So when you zoom into these patches, you have something that looks like this. Okay, so this is your dA. Okay, your dA that looks like dx dy. Okay, this, when you go radially outwards, what you have is dr, and when you make these arc lengths, you have r d phi, where phi is the azimuthal angle. Okay, so your dx dy look like dx dy's look like r dr d phi. Okay, and you can keep your dz's to remain the same way, and this whole integral over here, this triple integral, turns into rho all over m the triple integral of z dx dy that turns into z times r dr d phi dz. Okay, all right. So now look at the following. You can isolate this d phi over here because d phi isn't dependent on dr or on dz, right? So you can write that part as just d phi, the limits of integration being 0 to 2 pi, 0 to 2 pi because you're moving around the whole circle, right? And let's look at the rdr then. Okay, the dr or the integration of r along with limits of integration, you could see that the r in your cone is dependent on z, because as you climb up the cone, your r has a z dependence. Your r increases with increasing z, right? So we can find what that dependence is by drawing these triangles, where this is your r and this is your z. So you have basically two similar triangles, one triangle being this pink triangle and the other triangle being this yellow triangle. Okay. So if these two triangles are similar, you could write that the ratio of r over z is equal to the ratio of capital R over h. And you can write your r as a capital R times z all over h. Okay. So now that you have that, you can move forward with the integration. Okay. So you have that your small r is r z all over h, which means that you can replace this, right? You could replace this as to look like r squared all over 2. As r dr, and then you have z dz, right? Yeah. This limits of integration of r dr goes from 0 to rz all over h, and your limits of integration for z go from 0 to h, which is the whole height of your solid cone. And you can complete this integration. The first integral has the form of just 2 pi. The second integral, this r dr, looks like r squared all over 2 from from 0 to rz over h. And the second one, I'm going to leave that as z dz for now, because your first integral over here that I'm about to plug in has a z dependence. So when you complete that, what you have is rho all over m times 2 pi r squared z squared all over 8 squared with a 2 over here, and then you have the integral that goes from z to dz, right? Okay. Now the final form looks like, well, you can cancel out the 2's, right? And this is from 0 to h, of course, 0 to h. And this gives you the form r squared all over 8 squared, the integration of z cubed dz from 0 to h, right? And that gives you z to the 4th all over 4, right? From 0 to h, right? So that gives you h to the 4th all over 4. Yeah, h to the 4th all over 4. Okay. Now, all that we are left with is to find out the ratio rho over m. So, rho over m. What is rho over m? Well, we know that rho is mass over volume, right? So this is mass over volume. And when you divide that by this mass over here, what you get is just 1 over v. And the volume of a cone is given by the equation 1/3 pi r squared times h. Okay, so what you finally have is rho over m as 3 over pi r squared times h. Okay, now let's see what this looks like. This expression over here, you can cancel out the h to the fourths and the h to the 2 as looking like h squared, right? You have a pi over here from here, and rho over m is basically 3 all over pi r squared h, r squared times h squared all over 4, right? Now the pi's cancel out, the r squares cancel out, h squared and h cancel out to give you h, and finally you have 3h all over 4. So finally you have that the center of mass along the z-axis lies at 3h all over 4. And this is how you find the center of mass of a solid rigid object.